Hello everyone, my name is Iommi, PhD student at Medical University of Vienna, and if you don't understand Italian accent, apologies. I'm here to show you our work where we use deep learning to facilitate PET-driven motion compensation for FDG dynamic PET brain studies. But why do we want to do a PET-based data-driven motion correction? To answer with this question, we need to go back to our previous work on non-invasive absolute quantification. The software AquaPy utilizes in a synergistic way both the structural information of the MR and the functional information of PET data from an integrated PET MR system to produce cerebral metabolic rates of glucose maps. The pipeline is fully automatic and it is meant to help clinicians in the diagnosis of epilepsy. AquaPy was developed for an integrated PET MR system, but it would be more valuable if we translated it to a PET-CT, which is much more widespread and less expensive than a PET-MR. To perform non-invasive absolute quantification, we need first to extract the image-derived input function. To accomplish this task, the key points of the pipeline are extraction of the blood-pure region, motion compensation, and partial volume correction. The delineation of the volume of interest for the blood-pure region and the partial volume correction can be performed with a PET-CT and an MR protocol without simultaneous PET-MR. The motion correction part of the pipeline is the challenging task to replicate for a PET-CT system. Why? Let's see that. In an integrated PET-MR, sparse MR navigators are required to detect motion, and we can apply the motion vectors to align the PET images. In the PET-CT, we can only register directly the PET images at different time steps to compensate motion. But this will not work, because as you can see from the graphs, the activity distribution of the PET frames during the scanning is changing, while in MR navigators, image information does not change drastically during the protocol. Standard registration algorithms do not work if the images have not enough structural and feature information. So how can we do that? To overcome this problem, we need a transformation to achieve constant activity over the time in PET images as well. We are looking for a technique which does smart Photoshop, preferably automatic. And recently, we came across this algorithm, which converts drawings to realistic paintings using a deep learning technique called CGANs, conditional Generative Adversial Networks. People have already used this for converting low-count PET images to high-count PET images. And we wanted to do the same for the early part of the dynamic PET series, because they resemble low-count images. Based on this, we developed PANDA, PET navigators using deep learning. The model is available online and you can check the QR code. How does PANDA work? First, we used MR navigators to detect brain motion. We applied the motion vectors to the PET images and we aligned low-count PET data at different time steps with high-count PET reference frame. Secondly, we trained the CGAN to perform the transformation from low-count to high-count PET data. Finally, we can apply this model to a PET-CT system. We are going to register the pre-processed PANDA images to facilitate registration for motion compensation. This was the available dataset with healthy volunteers. We performed artificial data augmentation to train the CGAN. Ground truth, arterial input function, and metabolic glucose maps were available. We tested our method on validation data, excluding the training data. PANDA can pre-process PET frames at time after 2 minutes of scanning, while the structural information inherent to very low-count images is insufficient to generate acceptable results. Nevertheless, our previous studies suggest that for very early time point, motion magnitude tend to be negligible. We validated PANDA by deriving first the image-derived input function, and we compare results without motion correction, with motion correction based on non-preprocessed PET frames, and with PANDA preprocessed PET frames. So, as you can see from the graphs, we achieved less than 1% deviation from the ground truth with our technique. After the image-derived input function, we derived the glucose maps, and we compared them with the ground truth. The group analysis showed that the absolute percentage difference was less than 5% for the glucose maps. The utility of PANDA goes beyond interframe motion, and To support this claim, we also perform intraframe motion detection using very short 5-second subframes. PANDA pre-processed frames look significantly better than the original 5-second subframes, which mar much more structural details. And after motion correction, we obtain images qualitatively superior than the motion compensated images or registered without the PANDA pre-processing. As you can see, the cortex is much more sharper after PANDA pre-processing and up with the registration. We also did a pilot study where we applied PANDA on PET-CT data from different vendors, and we obtained high count PET images without additional training. In conclusion, we do not believe that CGAN does magic, but a combination of smart in-painting and smoothing of the images. And we take this opportunity to say that we are interested to apply our method to different sites on different PET-CT systems to perform motion correction on clinical patients. If you are interested, please write us. The mail address is shown below, and thanks for your attention.